Hello, everyone. Okay, I see people are joining in. I think I'll get started with the introduction, and let's see. Let's admit whoever joins in. So yeah, hello everyone, and welcome to today's webinar, oHFM FPGA SOM standard, enabling connectivity at 64 Gbps or 112 Gbps PAM4 data rates. My name is Divya, and I'm a senior marketing executive at iWave Global. I'll be your moderator for today's session. Thank you all for taking the time to join us today. Following the momentum from our successful joint webinar with SGET last month, we are excited to continue the series through this collaboration with Samtec. Yep. As FPGA and RF systems are continuing to evolve toward higher bandwidths and faster data rates, maintaining reliable high-speed connectivity and signal integrity is becoming increasingly critical. So that's what we are going to focus on this session about how the OHFM standard and advanced interconnect technologies are helping address these challenges. Before we dive in, just a quick housekeeping points which I would like to highlight on. This session is being recorded, and we will share the recording with all registrants after the webinar. Also, please feel free to submit your questions anytime through the Q&A section. We will address them towards the end of the session. Okay, let's move. So yeah, let me quickly walk you through what we have lined up for today. We will begin with an overview of the challenges that are faced in modern FPGA and RF systems and the SOM architecture. From there, we'll move on to the introduction and along with iWave, oHFM portfolio, and what is our roadmap looking like. If you'd like to understand more about oHFM and when it was introduced or why it was introduced, its ecosystem benefits and variants, I would encourage you to check out our previous webinar in collaboration with SGET. The webinar link will be shared in the chat window. Okay, so then we'll move into understanding how 64G or 112 Gbps PAM4 data rates are enabled, followed by a deep dive into the oHFM connector variant. We will also cover high-speed interconnect challenges and the solutions that are enabling high-speed connectivity. Finally, we'll conclude the session with a live Q&A. I think with that, let us get started. Over to you, Shamim.
Thank you, Divya. Hello, everyone. Myself, Ahmad Shamim. I'm working as an associate director at iWave. I have more than 15 years of experience working in SOM ecosystem, starting from SOM designing and development, also SOM-based record system designing and qualification. So, from the agenda, let's start understanding the challenges faced in the modern FPGA and RF system design. So today we see like rapid growth in the area like high-speed connectivity, advanced computing, and also electronic warfare systems. This increases the demand for FPGAs-based solution where high performance and faster bandwidth are supported. So FPGAs are no longer a simple programmable chips. Now FPGAs are packed as a SoC where program logic are tightly integrated with ARM core and AI core, RF data converter, and high-speed transceiver. Also, we see continuous growth in FPGA's module size and power requirement. with increasing as increase the demand for higher number of uh, like higher number of logical cells and transceiver channels and IO requirement. With this increasing complexity, that there is a demand for highly skilled resources to build a robust system. And the second, the earlier in low speed system designing, the connector merely act as just an interconnect which is used to connect from one layer to other. But as the speed increases, the data rate moves from 56 G to 112G PAM4. Since PAM4 are more sensitive to the noise than the traditional NRZ signals, the connector, the PCB traces, wires, and even the PCB materials is just a part of the high-speed system, high-speed signal path. And everything need to be taken care for a good quality and overall system performance. Because of this, the signal integrity and PI validation become mandatory part of the current high-speed system design. As design become more complex, the challenges increases that it takes more time and effort to develop a quality and robust system. But market is looking for a faster development and qualification. Also, since the most of the FPGA-based systems are designed for long-term, long product life support, but in the current time, that electronic ecosystem, electronic supply chain instability, managing procurement and also managing the product life cycle is a big major task. By analyzing these challenges, FPGA-based system design companies started looking for the SOM-like approaches. So where like FPGA is placed in a small PCB and all FPGA related power, clock, memory circuit are taken care so that they can just buy a off the shelf FPGA module and plug to their credit card and directly start working. Similarly, when we go to the challenges, so as the SOM demand increasing, but the current, if you see the challenges faced in the SOM architecture, we can find many industrial standard SOM architecture when it comes to ARM and x86 platform. For example, SMARC, OSM, and also COM Express, COM HPC. But when it comes to FPGA SOM ecosystem, so we see mainly a proprietary SOM standard, where SOM solutions are tightly linked to a single SOM supplier. Once the product is built around one of these ecosystem, shifting to another ecosystem become like a little difficult and also costlier. Another major issue is the lack of a strong second source. In case the SOM vendor stop supporting or like call for end of life or increasing the price, the system design companies is left with very few options. Because of this, even though SOM helps in speeding the overall development time, the ecosystem limits the flexibility to the system builders. Similarly, the scalability. So, like we can see different families from all the vendors, like uh, from Kintex, Versal, Agilex, but these are designed for different market need. When some vendors build a module based on these FPGA families, sometimes sometimes they differ in physical dimension or pin compatibility. Because of this, when customers upgrade a new FPGA generation, they can't directly use their existing carrier card. Instead, they have to fully redesign the board, and also they have to requalify. So this requalification takes the effort and the time, and also is delay the product to the market. So considering this, the SOM ecosystem where is not offering the smooth transaction. Also, one more problem we can see is the connector limitation. So connect today's systems run extremely high data rate, support interface like PCI Gen 5, Gen 6, even up to 400G Ethernet. At this speed, connector plays a crucial part of the signal quality. Even minor disturbance in the connector can cause signal problem like reflection and data error. On top of that, today FPGA platform need more transceivers, lane, and IOs, and also it demands for a compact size. So these type of compact connector were not available previously. And when it comes to the mechanical and the thermal challenges, the modern FPGA device consumes significantly more power. As the power increases, managing heat become a critical design challenges. Due to proprietary SOM's dimension, there is a limitation of off-the-shelf thermal solution like heat sink, heat spreader, fan sink. So it is very difficult to find the right solution when it to manage the thermal. And also, if there is a requirement for a compact solution, then it was very difficult to adapt the SOM. If there was a limitation on the height with the respect to the entire product dimension, so since the SOM has the connector with stacked height and very difficult to have without SOM, without connector SOM, so it was forced to they have to use a complete redesign the board. So, and one more point is like many FPGA systems, especially used in application like electronics warfare and defense, must undergo rigorous reliability test, and at the same time, there is a lack of standardized ecosystem to effectively support this requirement. By considering this limitation, industry was looking for an FPGA solution and is optimized the open SOM standard. And this is exactly where SGate contributed by driving the next generation open FPGA standard called oHFM. So let us understand more about oHFM. The oHFM stands for Open Harmonized FPGA Module, and it is the first open standard created specially for FPGA-based system on module. The standard was developed by SGate and iWave also actively involved in the initial initiatives. In fact, iWave's Vice President of FPGA Solution currently serves as the chairperson of the oHFM working group. Also, recently, iWave and SGate jointly hosted the webinar to officially introduce the oHFM standard. So, as Divya mentioned, the link is available in chat. Please go have a look. The main objective of oHFM is to establish unified and scalable architecture and enable a strong ecosystem for FPGA SOMs. The specification itself, like it was developed like not by one team, it was like one person. It was developed with the collaboration of different FPGA vendors, SOM vendors, and also connector technology partners. Even though during the connector selection process for oHFM, like Samtec team contributed closely with the ecosystem partner to ensure the connector interface and signal paths were optimized for the next generation high-speed requirement. Even connector pinout were defined in collaborate with the different SoC vendors, and also by considering the demand for different IO bank voltages, that also considered to enable the different variable IO configuration from the baseboard while defining the pin mapping to the and defining the pinout for the standard. Along with the specification document, oHFM defines a detailed design guideline for both SOM and carrier card. This guidance helps ensure consistent implementation and reliability. Also, it helps in the interoperability and across the different suppliers. So now, there are two variants of oHFM SOM. So one is oHFM.S is a solderable SOM. In this approach, the SOM permanently mounted on the carrier board and making it a very compact and cost-efficient solution. It is well suited for applications that require like enhanced security and mainly the tamper resistance and optimize the cost. The variant was primarily targeted mainly for the very low end FPGA to the mid range FPGA. And the second one is connector based. Yeah. So the connector based version. So this is a pluggable uh, to the carrier board using a high speed board to board connector, allowing the module to be easily installed and replaced even in the field. This gives customer flexibility to upgrade or downgrade the module as per their end market demands. So the next, so now we'll check the what is the oHFM's variant. So in oHFM, like we can broadly consider the four variant like size S, size M, size L, and size XL. So you can find the dimension of each sizes in the table here. So mainly that if you look at this left image, this looks exactly same as OSM. The main this look like mechanically it is similar to OSM specification, but electrically it is not aligned with the OSM. The intention is like the OSM is also a part of SGATE, and to utilize the ecosystem which is developed across OSM here, so like a socket and other supporting accessories. And also like you can see the highest the biggest size, that is 60 cross 45, so that can support with up to 4 high speed transceivers bank, one low speed transceiver bank, and one wide voltage IO bank, and four high speed IO bank. And it can support up to 50 watt of power to power the overall system. And the next is in the connector also we have four variant. So as you can see, so here the size S1 comes with one connector, and size S and size M comes with two connector, size L comes with three connector, and size XL comes with four connector. And with respect to the dimension width, so standard width is considered as 75. Considering the market during the market study, we decided to make a 75 as the standard size for the connector, and we also give a provision to extend the size to up to 95, and we call it as a extended version of size S, M, and L, and also SL, XL. So here with the connector one, we get one low speed transceiver bank and power control signal, and FPGA and other basic interfaces. Connector 2 adds the additionally three high-speed transceiver bank, and connector 3 adds 6 high-speed transceivers, and connector 4 additionally adds 7 high-speed transceiver banks. So totally we can get 16 high-speed transceiver bank from size XL. Also, some of the like if we are going for the like RF based SoC, so there is a alternate alt function which is defined as part of the spec, which allow us to take 8 ADC and DAC channel from connector 3, and also 8 ADC and DAC channel from connector 8, connector 4. So why two different connector approaches is used in oHFMC? The objective of oHFM is mainly to achieve the scalability and the cost optimization. Like if we use only one connector, either we have to compromise on the performance or cost and area. So if you see here, this connector width and this connector, So like these two are designed for different market requirement. So this is derived from ADM6 version series of Samtec connector, and this was the second, the bigger connector was derived from APM6 family of Samtec connector. So since it was target for different requirement, for example, this uh, 320 pin size sizes and size M connector, it can support up to 32 gigabits per samples, whereas size L and size XL connector can support up to 64 gigabits per sample. So by understanding the requirement for both mid to low end FPGA and mid to high end FPGA, so we planned as two kind of connector in the architecture. Now, like we high level, if you look at the overall benefits of oHFM, so main advantage eliminate the vendor lock-in. So multiple vendor can develop a compatible module, and the second is standardized footprint. Carrier board can be reused from across FPGA vendors. And the third is upgradable path. Like easily we can move from, like if you have taken care of your carrier card, you can use the same carrier for lower version size S and also size XL. So based on the market demand, you just change the module, and using existing enclosure, we just have multiple price and multiple configuration of single system with a very limited uh, modification. Also, it enables to grow ecosystem, so that we can make a strong thermal solution and other required accessories. And also, the main objective is to reduce the overall development effort, validation cycle time, and time to market. So here, like we'll highly go through the some of the OHFM product roadmap from iWave. So we already have RTX UltraScale Plus and Kintex UltraScale Plus SOMs in sizes. Also, we are coming up with Agilex 5 connector-based size M module. And when it comes to solderable, we are working with the Spartan UltraScale Plus in size M solderable version and Agilex 3 in size L solderable version. And this G74 is the world's first oHFM SOM. So it supports like up to 308K logic cells, and supports 12 channel GTY with the 16 Gbps speed. So here two connectors are supported. The first connector supports 24 LVDS from HP Bank, 53 single-ended from HD Bank and JTAG. The second connector supports 48 LVDS pair from HP Bank. So this entire SOM is designed as per the oHFM size S, and it is qualified for industrial temperature gate from -40 to 85. And if somebody is looking for higher speed transfer speed, so we have a Kintex based uh, SOM where we can support 16 GTY transfer up to 32 gigabits per sample. So also you can note that it also support 475 K logic cells. So before handovering to Matt, so I would like to take a few minutes highlighting iWave's other broader FPGA SOM portfolio. So as you can see, we have Brain form factor, which mainly offer Agilex 9, Agilex 7, RF SoC, Versal Premium, Versal AI based SOM, and also we have Orion form factor based Agilex 7, Aria 10, Zinc Ultra Scale, Kintex Ultra Scale SOMs. And also we do have rent form factor based Agilex 5, Versal AI Edge Gen 1, Versal AI Gen 2, Spartan SOM. So main, you can notice that in all these connector, we are used Samtec high speed connector. So we are closely working with Samtec for more than a decade. So you can also visit iWave website to know more about FPGA SOMs offering, and also you can drop a mail. Our team is that they can help you in finding the right solution for your requirement. Yeah, that's it. By this, I conclude. Now the math will take from here. He will go through the connected technology which is used in OHFM form factor. Matt, over to you.
Thanks, Shamim. Appreciate the introduction, and as always, we appreciate the long time collaboration that we've had with iWave in their program. It's also been a privilege to work with the iWave team as we've continued to develop the SGET specification, and that's why we're so happy to be a part of this webinar series that iWave is sponsoring. So thank you for the opportunity. Just a brief introduction. I lead the technical marketing efforts at Samtec. Been with Samtec for 10 plus years, 25 plus years experience in the electronic components industry with design, applications engineering, technical marketing, and industry standards focus. As Shamim said, we just wanted to provide a little bit more detail on the connector technology that's used on SGET oHFM. So looking at the connectors a little bit more in detail, Shamim hit several of the high points. We just want to supplement that with a little bit more information to show why the particular interconnect technology was chosen for SGET oHFM applications. As Shamim mentioned, both the all connector technologies use 320 pins. They're high density, low profile, slim connectors, four row of contacts, so you get 320 pins in a very small area. We use a high density 0.635 millimeter pitch, so that allows us to get a high number of I/O pins in a very small area on both connector families. We'll talk about the difference in size in terms of the width of the connectors in just a moment. Something else that we've also added to the solutions is using solder column technology. When these families were originally introduced several years ago, we used solder ball termination, but solder column optimizes the processing of applying the connectors to the PCB. Solder column technology also improves alignment, especially as you're bringing up new form factors like SGET oHFM, and offers improvement, especially on crosstalk at higher speeds. Because these FPGA-based SOMs are sometimes going to be based in mil aero, industrial, or other rugged applications, we wanted to make sure that we had ruggedization features. So each connector, both on the receptacle and on the plug, have weld tabs and alignment pins. We'll talk about that in detail. Specifically, per the spec, the module connectors are the receptacle or female. You see that illustrated here. In the spec, we label those J1, J2, J3, J4. The module connector, the receptacle or the female, has a single fixed height to help simplify processing and to simplify SOM design. When you get to the carrier connector, that's the male. We don't have an illustration of that, but the carrier connectors, the mating connectors for the receptacles on the SOMs, are designated as P1, P2, P3, P4. There's additional detail on that within the spec. That's the SGET oHFM spec, and J1 goes to P1, et cetera, et cetera. The carrier connector does have two options, so that allows for a overall stack height between the SOMs and the carrier cards of either 5 millimeter or 10 millimeter. The advantage of using the 10 millimeter is that allows for higher density carrier cards. So you can attach components both on the top and bottom side of the SOM, and then with the 10 millimeter stack heights on the carrier card, you can put electronic components right underneath the SOM as well, as long as you stay within the component height guidelines that are outlined in the SGET oHFM spec. Shami mentioned a little bit of detail on the connectors, but just want to go into this a little bit more detail. On the size S and size M solutions, we have a very thin profile. It's a 0.96, 1.58, 0.96 millimeter row spacing, as well as a 0.635 column. That's the space between the pins. That allows for a 5 millimeter width connector. Again, that profile was chosen based on some Samtec Interconnect designs that we have in other applications. As we mentioned earlier, size S module connector J1 mates with P1, J2 mates with P2, and these are derived from the Accelerate HD ultra-dense slim body arrays that Samtec has commercially available. One question that comes up is, are the SGET connectors the same as the standard connectors within the Accelerate HD family? And the answer to that is no. We have customized these interconnects specific for SGET based on use cases, anticipated use cases of the oHFM modules. So just a little bit more detail on Accelerate HD. We're using 320 pin versions of the connector on the SGET oHFM specification, but the commercial product family supports anywhere from 4x20 all the way up to 4x100. Again, very slim bodies, 5 millimeter width, 5 millimeter stack heights. There's a little bit more flexibility in the off-the-shelf product family. We can support stack heights 5 millimeter, 16 millimeter, and we show the high speed because it can support PCI 6, CXL 3.1, and the like. We've already talked about the solder column capabilities that the solutions have. Getting into the size L, size XL connectors, we add a little bit more space in between the rows of the connectors. So it's a 2.2, 2.4, 2.2 millimeter spacing along the length of the connector. Again, we're using a 320 pin version here, 4x80, is similar to the size S and size M connectors. J3 mates to P3, J4 mates to P4, and again, as Shami mentioned, these are based on the Accelerate HP. Why the difference between the HD and the XP? Well, you can see in the illustration here this extra space along the axis of the connector. And what that allows for is additional grounding vias and differential signaling to be route either in an X direction or a Y direction along the connector. We'll talk about some of the benefits of that and how that simple design change between connector families is the main reason that you get that boost in performance from 64 gigabit PAM4 all the way up to 112 gigabit PAM4. Like the HD, 5 millimeter and 10 millimeter stack heights, we don't have these within the SGET oHFM, but if you're working on a custom solution, our Accelerate HP can support up to 1,000 pins per mated connector pair. These support up to 112 gigabit per second PAM4. We'll talk about why PAM4 is so essential here in just a minute. And we have other row counts in development. So this illustration also just shows you the density that this solution has. I like to think of Accelerate HD as the slimmest connector that Samtec has at 64 gigabit and higher, and the 112 is the highest density. So using a combination of these solutions within the SGET oHFM spec gives us the best of both worlds. There's an eye chart here, but this just lists all the orderable part numbers available from Samtec. This is available within the SGET oHFM spec. It's also available from the Samtec website. You can see the fact that we have the connectors identified by their placement on the SOM or the carrier card, the stack height, the weld tabs, and then the plating. We have a 10 micron and a 30 micron gold plating option on the pins depending upon your processing needs. So that's the connector basics. For the next 5 to 10 minutes, I just want to talk a little bit about some of the SI performance that's enabled by adopting good design technique, not only on the SOMs, but also on the carrier cards. You know, Shamim made a comment earlier about how improper connector selection and by extension improper connector breakout design can affect the signal integrity of the performance of your solution. When we say breakout region, what that is referring to is how you break out traces, vias, and grounds for the connector, both on the SOM and on the module. If good PCB design techniques and signal integrity design techniques are not used, that greatly affects the performance of the system. On the other hand, if you use optimized design, you can get long traces on an SGAT oHFM carrier card or an SGAT oHFM SOM and still get the performance that you needed. We typically view the mated connector set as an optimized, consistent transmission line. That's great as the signal passes through the connectors, but you also have to get the signal into and out of the connector, into and out of the FPGA, and using good design practice on your PCBs is essential here. So when it comes to breakout region design trade-offs, you want to optimize signal integrity, you want to ease routability, and obviously whatever you pick has to conform to design for manufacturing rules. And you also have to have ample spacing. Granted, in 10 minutes, we're not going to make everyone a high-speed design specialist, but we at least want to show you some of the technology and some of the capabilities that have been ingrained in the SGAT oHFM spec and also that are available from Samtec from a technical support standpoint as you embark on your oHFM designs. Design constraints, these are other design choices that engineers have in their toolbox as to how they can optimize their SGAT oHFM performance. What are the limitations of the design? What routing direction are we going to choose? We'll talk about that in just a moment, how that affects performance, how that affects some of the design choices you have. Are you going to put, when it comes to high-speed design, Shamim mentioned that the one of the iWave SOMs will support 32 gigabit transceivers based on the FPGA capabilities. How you ground that and how you pin out the connectors affects that performance. We'll show some of the selections that were made within the SGAT oHFM with those speeds in mind. Grounding vias will show how to optimize that based on your needs. Signal vias, again, we'll illustrate briefly some of the options that are available on the connectors, both on the small and medium as well as the large and extra large. And then how do we handle fan out and via stub length? So a lot of design techniques, design selections go into optimizing the SI performance. This is sort of an eye chart, but I did want to show, this was taken directly from the SGAT oHFM spec. So you'll see from some of the transceivers, there's a ground, there's the two differential signals, a ground, and then two differential signals, another ground. So this could be this is a receive, a transmit, and the like. For some of the higher speed signals, you need additional grounding. So it's literally signal, signal, ground, ground, signal, signal. We'll talk about that here in just a minute. Depending upon the pinout, depending upon the functionality, the SGAT oHFM pinouts, we're not going to get into this because that's actually up to 1,296 pins, 1,280 pins if you're using the XL modules. All that detail is contained in the spec. These are just snapshots of some of the signals that were contained there. So what does that mean practically? These next 6 slides show some of just briefly, show some of the trade-offs that are made when selecting pinouts, how you ground, and how you route your signals away from the connector. So in this instance, in Samtec language, we have a single ground between the pins. So you can see this is a differential pair here. This is a ground differential pair. Here, make sure I'm using this. So you have a differential pair here. This is a ground. You have a differential pair here, differential pair here. That's a ground, differential pair, differential pair. So you have ground, signal, signal, ground. In addition, in this instance, what we're doing with the signaling is routing everything through a vertical escape. So you can see that the signaling is traveling in this direction. away from the connector. So in this particular instance, some of the pros is that this allows for the densest routing on the size L, size M connectors, the ADX6, but this also has a trade-off of routing signals between vias. Going to the next slide, the difference here is instead of, you still have ground, signal, signal, ground, but instead of routing signals in one direction, you're routing signals in two directions. So up and down in this image. So the pros of taking this approach: less routing layers used, better crosstalk, simplify the grounding, but again, the con, you have routing necessary in between signal vias. Another option is routing the signals along the length of the axis. You can see again the routing is to the left of this image. The pros of using this approach: identical routing on all layers, but again, the routing is limited by the number of signal layers in the PCB. Next, going from a ground signal signal ground to a ground ground signal signal ground ground. This allows for improved SI performance. You can see that using this system, again, you're using double ground through row with the escape moving the up direction of the signal flow. This offers the best through row performance, but it's less dense than a signal ground. Another approach is using double ground with mirrored approach. So again, you have signals flowing in each direction along the long axis of the connector. This offers the best overall performance, but it's the least dense from a escape standpoint. And then again, ground signal, signal ground, going ground lengthwise. Pros to this: identical routing on all layers, but the routing is limited to a number of signal layers as well. So, there's a lot of data there. And again, we're not going to make USI design experts here in just a few moments, but I did want to mention, what this looks like from a practical standpoint. So Samtec has a history of, when we develop a new interconnect technology, we also develop a test platform that we make available to customers. Not only do we provide the simulated data, but we also provide measured data. So this is the just the insertion loss and the return loss of mated connector pairs for the size L and size M connectors. And you can see at, let's call it PCI 5, 32 gigabit per second, you have a Nyquist at 16 gigahertz. So right here, you have an insertion loss of about 5 to 6 dB. Given that the overall channel length, or the overall channel loss of PCI Express at PCI Express 5 is 36 dB, the mated connector set in the breakout region only have 6 or 7 dB of loss. So that means that gives you an additional 30 dB of channel loss where you can route signals across the system. Same thing with return loss. We always look for a number below 10 dB. So here at 16, you're fine. If you look at PCI 6, PAM4, that's also using the same Nyquist. So this data shows that both on the insertion loss and on the return loss, that the connector is fully capable of supporting PCI 6 performance over long channels beyond which are realizable with an SGET oHFM. Just briefly, looking at the size LXL connectors, again, there's multiple termination options. You go signal, ground, ground signal. Typically on these connectors, because they're higher performance, you're going to have signal, signal, ground, ground, signal, signal. There's different ways of routing the pins, orthogonal, routing them lengthwise. It really based on use case. Our signal integrity experts are here to help your team make selections. We've worked collaboratively with iWave, and we also continue to work with SGET oHFM and other SOM vendors along these paths as well. So again, just some IL, RL specifications. So at 112 gigabit, we're looking at a Nyquist of 28 gigabit. So that puts us about right here. The insertion loss for the connector, mated connector set plus the BORs, you're right around 6 dB. And then when you look at 28 dB right about here, the return loss is below 10 dB. So again, these are very quick back to napkin SI performance metrics, but it gives you, the listener, confidence that both connector options work as advertised within SGET oHFM use cases. So takeaways from Samtec's part, the SGET oHFM connectors support high-speed connectivity with rugged features, low-profile, high-density form factors. We backed it up with our field application engineers, our application engineers at the factory, and our signal integrity engineers to help optimize performance for your SGET oHFM designs. All connector part numbers are fully released from Samtec, and they are or will be soon available from multiple distribution partners. And then you can contact Samtec at any of the information here provided via email or website. One last thing I did want to mention before I turn it over to Divya for the comments. Please get involved with SGET oHFM. The base spec is out. That was released in January. We're currently working on the carrier design guide, and we welcome all input from all SGET members. That's available. The spec is available on the SGET website at the link provided. You can also follow SGET on LinkedIn as well. So I'm going to turn it back to the email, the QR code, get you in touch with the SGET management team, and they can provide additional support on how to get involved with SGET. I'm going to turn it over to Divya, and she'll go through the Q&A section of our presentation now.
Thank you, Matt. Thank you for sharing valuable insights into high-speed interconnect technologies. I think we are running a bit late, so we'll just quickly see one or two questions, and then I'll make sure that the rest of the questions are answered through offline. So yeah, let's see what we have first. Okay, I see a question which says why oHFM connector size S and M have different module sizes, even though the connector setup looks similar. So I think that's a question about SOM. So Shamim, would you be able to answer that?
Hello?
Yes, you're audible.
Yes. So, so as you can see, like, yeah, that so both supports like same sizes, like 75 cross 50 mm. So, but what are the connector we use? It is like very dense connector. Each connector supports like up to 320 pins. So like some of the FPGAs are like size are bigger. Sometimes like the SOMs wanted to have more RAM. So that time the one connector is sufficient, but we may need extra space to accommodate more RAM memories or extra circuit. So considering that the unique requirement, we also introduced that like separate S with one connector and one with this same two connector with the little extra size width and length.
Okay.
So yes,
You want to add anything, Shamim?
no. So they can see here like yes, that's it.
Yeah. Okay. So let's see what we have next. There's one related to connectors. I think it is for Matt. So, what are some ruggedization features of oHFM connectors, and why are these added?
Yeah, so we touched on that briefly, but in essence, the alignment pins are added to help keep the connectors within tolerance. One of the reasons we're concerned about alignment is in high density multi-connector applications like SGET oHFM, we want to try to minimize the tolerance stack up. So the alignment pins help do that. Adding the weld tabs helps with ruggedization. When there's 4 connectors, you can imagine there's increased mating and unmating force. And while these are rugged interconnects, if you get into a high cycle, mating cycle application, the weld tabs are going to help secure the connectors and both the weld tabs on the carrier card and also on the SOM module or the SOM are going to increase ruggedization. That the weld tab feature we implemented in COM-HPC, and we found that when the weld tab was implemented there, that greatly increased the regularization of the SOM. So that was really a best practice that SK oHFM borrowed from the COM-HPC ecosystem.
Thank you, Matt. So let's see one more question. There's a question which says, how has the response been for iWave's oHFM connector-based SOM so far?
Yes. So the module has recently launched, and yeah, we have good response so far. We also received PO, and we're expecting to get more POs in coming days.
Okay, thank you. Then I think we have exceeded our time. I'll just take one final question before we wrap up. Matt, there's this question which is about the connectivity, which is, can you support faster than 64 or 112 Gbps PAM4 data rates on these connectors?
I would say yes, with the caveat that you're going to be limited in the trace length that you can get on the channel. So it all depends upon the channel noise and the requirements of the signal that you're trying to implement. But whoever asked that question, please send an email to sig@samtec.com with your specific application solutions, and we can help you through that use case.
Thank you for addressing that, Matt. All right, we're just about to end our scheduled time. I think we have exceeded that. So the questions which are unanswered, I'll make sure that I'll answer them offline. Before we conclude today's webinar, we would also like to highlight a few upcoming industry events where iWave will be showcasing oHFM-based SOMs and solutions. So you can meet our team at FPGA Developers Forum in the coming week, and FPGA Conference in the month of June, and also FPGA Horizons in the month of October. So if you're interested in learning more about our oHFM solutions and FPGA SOM portfolio, we'd be happy to connect you with connect you during the events. So yeah, alternatively, we request you to reach us anytime at mktg@iwaveglobal.com. Thank you once again for joining today's webinar. We hope you found the session informative and valuable. Have a great day ahead. Thank you. Thank you so much.